So I assume you agree to be recorded.
Yes.
Otherwise you have a problem. So it's great to see everybody here in person. So Henry is a PhD student at Stony Brook University, a small school somewhere on the East Coast. And he has two things he's doing. He's one of the main builders of the S-Phoenix time projection chamber, which is really coming into reality now. His advisor is Tom Hemmick, and he's working closely with Tom on that as a major project. And in addition, Henry, together with Letitia and a few other people and myself, we kind of got interested in thinking about event shapes and that sort of thing for an EIC, and we contributed to the EIC yellow report on event shapes, extraction of alpha S, and then we started thinking, well, maybe one can do something a little quicker than 15 years from now, and then we got into the H1 experiment. Ben and company independently arrived at the same place, and now we are working on H1 data, and that's what Henry will tell us today. So Henry got his undergraduate at the University of Illinois at Champaign-Urbana, now graduate student at Stony Brook, and he'll tell us what he's doing on the H1 experiment.
Yes, so thank you all for having me. It's fantastic to be here, to see faces in real life. That's kind of great. So, and also if you're interested in the S-Phoenix TPC, I'll also plug, I was kind of recruited to give an INPA talk next Friday, where I'll kind of focus on that if any of you are interested. So yes, so this talk will focus mainly on kind of a new analysis that we've been doing using archived H1 data. Can I change my slide? Yes. Okay, so the first part of my talk, I'll kind of go through the history of HERA and H1 because, at this point it's kind of, old, kind of forgotten territory. Then I'll talk just kind of briefly about inclusive DIS and some of the important aspects about it when you're doing a measurement. And then I'll talk about kind of the meat of the measurement, which is groomed event shapes and some of the ideas around that. So HERA was an electron-proton collider at DESY in Hamburg. They had both electrons and positrons. The beam energies were 27.6 GeV on 920 GeV protons, delivering around 800 inverse picobarns, mostly to the two general purpose experiments, H1 and Zeus. And interestingly, for the data preservation aspect of it, HERA kind of ran at this golden age, right, where we had an E plus E minus collider at high energy, we had LEP, and then we had a PP collider of high energy at the Tevatron, in addition to HERA. So, kind of keeping that in mind, HERA was actually kind of overshadowed for the most part by those two kind of gigantic undertakings. So HERA was kind of divided into two different run periods, HERA 1 and HERA 2. In 1981, they kind of came up with a proposal to turn Petra, who had just recently discovered the gluon, into an injector for an electron-proton collider. And then about 10 years later, very quickly, only 10 years later, they had a brand new EP collider providing first collisions. They installed spin rotators for the lepton beam in 1994, and then kind of two fixed target experiments, Hermes and HERA B, turned on in kind of short succession after one another, somewhere around the era I was born as well. Then in 1998, they increased the proton beam energy by 100 GeV and shut down for an upgrade in 2000. So in the HERA 2 run period, on top is kind of some of the theoretical ideas that kind of came into their own during the HERA 2 run period. And the HERA 2 run period was kind of in the beginning characterized by like horrific backgrounds that really for the first 2 years rendered it almost that data is almost unanalyzable. And I can talk a little bit more about what the actual sources of the backgrounds were if people are interested for EIC as well. And kind of during that time, a lot of physicists actually left for the LHC, which was coming online, in due time. And then between 2003, they finally got the beam background sorted out, and they collected around 400 inverse picobarns of data between 2003 and 2007. Then kind of after, yeah.
What was that a surprise, that background?
Oh yeah, absolutely. I mean, it was kind of the accelerator scientists, did their simulations, and then even until 2007, they never really had like a deterministic model that could predict exactly where the synchrotron radiation of the electron beam would go. So it was kind of like a, guess and check, send the beam, this way, that way. So yeah, I mean, it was very much a surprise. And the experiments, it took them 2 years of very dedicated hard work to figure out a sustainable kind of running condition for the experiments. So anyway, after 2007, kind of a lot of the main results came out. The first iteration of HERA PDF, which probably some of you are familiar with, came out in 2009. In the 2009 to 2012 period, DESY actually invested a lot of money into data preservation for these two experiments. That was kind of ongoing since then, all the way up until the present. In addition, kind of in 2015, so even at that time, that was pretty significantly after the end of the shutdown, is the most cited HERA paper, which is the combination of the H1 and Zeus inclusive cross-section measurements. And then in 2020, H1 actually underwent this like complete overhaul of the software, C++ 17 and Python analysis and root 6. And so it's like an extremely modern analysis framework that they have available for the future, EIC related analyses or, new techniques that, people in this room are coming up with to look at the data in a new light.
Would it be more comfortable to stand up and kind of point with this? I think.
Yes, I think that the difficulty is that I have to change my slides as well.
Well, why don't we just do it like this, and then you can just, hit the arrow. How's that?
Yes.
That work for you?
Yes. I'm very happy to, get to use this fantastic instrument that we have.
Stand over
here.
that side, because you're kind of in front of your slides there.
Okay.
Good. All right. How's that?
Come over.
That work for you?
I might be blocking James.
Very modern setup.
Oh yeah, fantastic. All right. So H1, the HERA collaborations kind of began to form in October '84, around 5 years after Petra discovered the gluon. So really, very quickly after that kind of success, they were kind of thinking forward about the next future. So Zeus formed largely of members of the Tasso experiment, which is one of the 4 main experiments at Petra. They kind of had the idea that for these high energy at the time EP collisions, what you really wanted was a compensating uranium scintillator calorimeter as kind of the centerpiece of your experiment. H1 formed of kind of everyone else. The other 3 Petra experiments, as well as people from EMC and BCDMS at the SPS. And they kind of nucleated around this idea that what you want is a high resolution liquid argon calorimeter. And also their dislike of the people from Tasso. And both of these detectors were kind of designed largely by, high energy physics was, kind of the name of the game. Because at that time, people weren't as pessimistic as we are these days about finding new phenomena. So, they had things like leptoquarks, SUSY, heavy leptons, heavy WNZ. And so for those kinds of analyses, what you want is kind of the ability to reconstruct the invariant mass of, very powerful, strong jets. And things like hadron ID were not kind of the focus of these experiments. It was really, they were looking for very striking high energy signatures in general. H1 focused a little bit more than Zeus on neutral current DIS. Zeus was kind of more specialized in charge current DIS. And these detectors are kind of both really fantastic for jet studies, which is great for us. And H1 has around 1 billion events in total on tape. So the centerpiece of H1 is really this liquid argon calorimeter. You can see kind of a nice kind of cutaway of it here. So the proton is coming in this direction, the electron is going in that direction, and the cryostat couldn't really go in both directions because of how do you install the detectors inside of it. And actually, an interesting historical fact about H1 is that they actually had originally planned to not have any kind of calorimeter whatsoever in the backward direction, which would have been a very interesting choice because they basically would have then only recorded the scattered electron for very high Q-squared events above like a Q-squared of 100. And they basically said, who cares about physics below a Q-squared of 100, right? Who could possibly care about that? And these days, of course, that's kind of a very interesting and important region for us. And they did actually, in fact, upgrade their backward calorimeter to be higher resolution than the initial one. And then they even added a hadronic calorimeter behind the electromagnetic calorimeter in the backward direction. And so the resolution of these calorimeters was actually fairly good even by modern standards. The EM resolution is not the best, but the hadronic resolution is still kind of competitive with modern hadronic calorimeter designs. The tracking of H1 was done in the central region by some kind of old school drift chambers everyone knows and loves, with some kind of in between MWPCs to give things like timing resolution and to locate tracks in Z, because really the drift chamber, the central jet chamber, really kind of gives you a precise measurement of R5 but not Z. So they had some kind of interleaved stuff there, and really these detectors were all very, very thick in comparison to what we're talking about for EIC. In fact, basically the supports of these central jet chambers were so thick, and you need it to hold the tension of a huge number of wires in a drift chamber like this, that really the forward and backward tracking detectors never really worked quite right, because it was extremely difficult to calibrate when the electron is passing through the material of the end plates of the jet chamber. Also maybe interesting to this audience is the central silicon tracker, which unfortunately kind of experienced both a larger than expected radiation load and had a lower than expected radiation tolerance. And so it also kind of never achieved its kind of full potential. The larger than expected radiation load actually aided in one analysis in H1, which was the analysis looking for magnetic monopoles that had embedded themselves in the HERA beam pipe. And so you take the beam pipe and you pass it through a squid magnetometer and look for a monopole. So that's one place where the radiation helps, but in general, it doesn't help. Okay, so now to kind of move on to data preservation. This is a very interesting kind of historical note on kind of some of the very first example of data preservation. Is this really fantastically interesting document that was written in the later Han period in China, and contained in this extremely lengthy text is actually reference to a guest star that is described in rich enough detail for modern astronomers to actually constrain this as having been a type 1a supernova whose evolution lasted X number of months, and was in Alpha or Epsilon Centauri. And for this is kind of a fantastic example of what we can kind of hope to do, right? Because creating and maintaining those kinds of manuscripts certainly was expensive, and probably people at the time said, oh, why should we maintain these records, right? And they could never have known the impact that their document would have on the far future. And let us kind of hope that.
Can you make sense of what's written?
Part of it, I think. It's still this tradition of mainland China, so we use to simplify, so.
Yes. So, let's kind of hope that in the 41st century we can revisit our data and have it be useful as well. So as far as H1 goes, this effort started in around 2009. And also there's this kind of global collaboration called DP4HEP. And really a lot of the main players in that collaboration are from DESY and even H1. So this is kind of one of the reasons why the H1 data preservation is really kind of so top tier. The goal is kind of this level 4 data preservation where you can literally revisit the data, revisit the raw data, and do a complete analysis kind of from scratch. And even analyses such as the charge particle multiplicity distribution, which is very kind of dependent on low level information. This was done by Kong and some others in 2020. And this is kind of the first analysis by non-H1 typical people. And you get very nice plots from that. And additionally,
how did you exactly preserve? You transfer all the data from tape to hard drive?
Yeah, I believe it was, yeah.
Okay.
And can I?
Yeah.
And how much of a data pipeline, how much cleaning of the data do you have to do to make it usable for future generations?
Well, that's kind of a good question, right? There's a model which says, save literally everything, anything that you could conceive someone possibly, using someday. But of course, I mean, it's an interesting thing also because, you know, the capability of humanity to store data, you know, where when these experiments were written, like a megabyte was a huge amount of data, right? And now, you know, terabytes is kind of a hard, you know, pocket drive.
Is there a question online? Otherwise, everyone, please mute if you're not asking a question. There's a bit of background noise.
I don't see hand.
Okay.
But maybe there's another kind of way to ask that question is if you want to do, I mean, if you take data, you have an immense data set, and then every experiment, you gotta kind of go through it and say this run is good, this run is bad, there's a problem with the detector. So you have to do a QA on the recorded data set. And well, maybe you can comment on that. That's already been done for us, basically, so. Because,
But that even data qualified as kind of bad is still available. So they really kind of saved, you know, basically everything.
And I think the difference between this and a lot of others is a lot of experiments, you can go back and find the raw original data. But if you just get that file, you have no way of knowing what any of it is, what you're reading out. So you need that entire electronic channel by channel description of the data. And here, of course, they have that, but it's also processed in a way you can just grab it and use it as is.
Right. Yeah. I mean, it's like a running, functioning collaboration. They kind of maintained the collaboration aspect of it. And I think that this effort kind of provides us an excellent opportunity, you know, in this age of kind of focusing on, you know, one collider at a time, to, you know, study jets across collision systems. You know, with, you know, this effort is also kind of involved in resurrecting the LEP data. I mean, even Petra has kind of been mentioned in the DP4HEP or the DPHEP community as possibly being resurrected. And, you know, we have a wealth of PP data that could also, you know, quite easily be compared to this data as well. So here's kind of an interesting historical plot, a cute one. So HERA turned off in 2007, and this is talks, number of talks per year on the y-axis, and then year on the x-axis. And you can see this kind of negative, it's around negative 13 talks per year was the slope. However, the EIC yellow report has actually kind of reversed that trend, and with H1 kind of contributing a large fraction of the talks since 2020. Okay, so now to physics. You know, obviously important in doing DIS analyses is the DIS kinematics. You know, these kind of familiar variables completely specify the kinematics of an event, the exchange boson virtuality q squared, Bjorkane x, and the inelasticity y, which you can measure, you know, with just the scattered electron if you would like, or just the hadronic final state if you would like. But in reality, you always achieve, you know, kind of a better precision by combining all of that information as best you can. Also important for kind of the next bit of the talk is the bright frame, which is defined as the frame where more or less the incoming quark comes in with x times the proton beam momentum, and then it leaves with basically negative of that. So at Born level, this basically corresponds to the frame where the proton continues. So the proton is coming at positive infinity in eta, in pseudorapidity, and then the struck parton leaves at negative infinity in pseudorapidity. And this is kind of a somewhat natural frame for jet finding, because what you have is a large kind of geometric separation between the struck parton and the beam fragmentation. You know, the struck parton is at minus infinity at Born level, and then the proton remnant is at positive infinity. So, you know, you can kind of dice this up however you'd like to find jets, however you would like. So at Born level, of course, you know, being at eta minus infinity, what that means is that, you know, you have 0 PT. So in the bright frame, the kind of single jet style event has almost no PT. The only PT is coming from, you know, kind of random hadronization effects or intrinsic KT in the proton. However, where you do get large PT is from these kind of, you know, hard gluon radiation that kicks the kind of struck parton, to one side or the other, and then you can get some large amount of PT. So the old school kind of HERA jet analyses, what they did was they looked in the bright frame, and then they actually used anti-KT, which will never find the Born level process, but can with relatively high accuracy find the kind of next leading order hard gluon radiation, and then you can use that to like constrain alpha S and things like that. So to talk a little bit about QED radiation, because it's kind of an ever-present annoyance when you're trying to do these kinds of measurements. So you can have QED, a photon radiated off the incoming electron, which effectively reduces the root S of the collision because the electron beam energy is then lower. You can also have final state QED radiation, where the scattered electron after scattering releases a photon. The QED ISR is typically more challenging to deal with because it more or less just goes straight down the beam pipe and you don't reconstruct it. The final state radiation is not so much of a problem typically because it's typically collinear to the scattered electron, and it kind of just goes into often the same calorimeter cluster as the scattered electron, and you don't have to worry about it so much. The thing where you can get into trouble is if you're doing a measurement in the bright frame. Any issue in reconstructing X, and basically every particle is in the wrong place, right? Because you've reconstructed the boost incorrectly, and then you do the boost, and every particle is kind of not where it should be. So you really need to do these bright frame measurements. You need the DIS kinematics reconstructed very precisely. You can do that by effectively measuring the effective root S of a collision event by event. So you can do that by kind of exploiting the fact that longitudinal momentum in an event should be conserved. So the typical way of doing this is you have, you take the sum of the E minus PZ, which for a particle going directly in PZ is basically 2 PZ. And for a particle going in having positive PZ is basically 0. And therefore being insensitive to hadrons that are lost in the forward region because, the proton beam remnant goes down there and you typically don't see much of it at all. So you don't want to be sensitive to that because then you'll kind of be messed up. And what you can do is actually you can cut on this quantity. And by doing that, you're kind of removing these radiative initial state events where the ISR photon has carried away a significant amount of the longitudinal momentum down the beam pipe and you didn't measure it. And you can even use this E minus PZ quantity to directly infer what the actual kinematics of the collision were. And this is kind of called the sigma method, or the case where you don't assume that the center, S, square root of S, is actually square root of S. That's called the I sigma method. And that's what we use in this measurement. The other kind of annoying effect of QED radiation is that these photons tend to fall around eta equals 0 in the bright frame. So struck parton is at eta of minus infinity, proton beam remnant is at eta of plus infinity, and you have these photons that tend to fall at very high PT. So if you're looking at anti-KT jets or something, you can very easily get confused and say, oh, there was a 5 GeV photon there, it could be a jet. So you need to kind of treat that properly.
Sorry, but I thought final state was collinear.
Yeah, it is. It is. So when you do the boost to the bright frame, so this is kind of a poor, a graphical representation. So the photon radiated off of, so the electron actually also falls at eta of around 0 in the bright frame. It's really kind of the hadrons that are geometrically separated, but the electron tends to fall around eta of 0. And so both the initial state radiated photon and the final state radiated photon tend to fall around eta of 0, which you have to then somehow, deal with them. The ISR photon you typically don't measure it anyway, so it doesn't really affect your measurement. But if you're doing like a comparison to an event generator or something like that, you need to make sure that that's handled properly.
But like you said, it affects Y. it changes why.
It changes basically
Everything.
all the, it changes kind of everything. Or the final state radiated photon, it doesn't affect like the kinematics of the collision per se, it affects how you reconstruct them. The initial state photon actually does, having radiated an initial state photon actually does affect the kinematics of the event. And then also that photon can, if you accidentally say that's part of the hadronic final state, then you're kind of also confused. Okay, so now we move on to talking about event shapes, which are kind of some of the very earliest kind of QCD observables. It's really just, you take every particle in the event, and in this case, this is a measurement from H1 of the thrust distribution, and it's basically just how much PZ, how much momentum, how collimated are you along kind of the thrust axis, which in this case is basically just the Z direction in the bright frame. And you see, it just pops right out at you, right? Like the running of alpha S is just kind of, so 0 is a very kind of collimated event, kind of one jet collimated event, and tau of 1 is kind of like a dijet event or a multi-jet event, where it's not very collimated along kind of one direction. And you see, Q, you have like, as you go in Q, you get more and more collimated, and you verified QCD and you're very happy. And in addition to being sensitive to things like alpha S, you're also sensitive here to things that you can predict, like in soft collinear effective theory. And in addition to that, even you're sensitive to things like hadronization in this peak region. And these observables have been used like very extensively in E plus E minus and bright frame EP collisions, because the current hemisphere, the struck parton hemisphere of the bright frame, is to first order basically one hemisphere of an E plus E minus event, and that's kind of one of the significant benefits that you gain in the bright frame.
There's a question. There's a question from Barbara.
Yeah, I actually have a couple of questions. So I'm a little confused because shouldn't the thrust for a dijet event, multi-jet event look different from one another?
Yes. Well, what do you mean, I guess?
Well, if you have a dijet event
Mhm.
and you have the kinematics fixed, then isn't that going to have a different thrust value than if you have a 3-jet event or a 4-jet event?
Yes, but kind of, first thing is that like the 3 and 4 jet events are relatively rare, and they all they share in the sense, they share the same kind of region of phase space in the sense of they're not single jet events. So it's very hard to distinguish a 2-jet from a 3-jet event based on the thrust, but you can distinguish like a 1-jet event from a 2 or more jet event.
I guess a 1-jet event is going to have a thrust that's close to 1, right?
It's the opposite by virtue of this convention of them subtracting 1 from the distribution.
I see. And so you also mentioned something about the peak region, but I look at the spot and I don't really see what you mean by the peak region.
Yeah, so the peak is like the tau roughly equal to 0 region of these.
I wouldn't have called that a peak, but
it's a log scale. So if you look at it on a linear scale, it is very kind of strikingly a peak. Any more questions? All right.
Yeah, move on, please.
Sure. So now, kind of to throw another thing into the poll, there is this recently proposed Centauro jet algorithm that does a very nice thing, which is that it actually captures the Born level jet in DIS, unlike the kind of standard lap frame longitudinally invariant anti-KT algorithms. It kind of isolates that struck parton with very high efficiency by kind of making the distance measure very, very small when you're kind of collinear to the exchange boson, and making it, having the distance measure blow up as you go in kind of the proton beam remnant direction. What we do here is we use Centauro to produce a clustering tree, a jet clustering tree of the full event, where kind of these guys are clustered last and these ones are clustered first. And then, so if you're using Centauro as like a jet algorithm, this is kind of, there's these nice event displays that are a little bit hard to read. So kind of this direction on this plot is the struck quark direction. And then alternatively, you have the
Can
proton.
you please, oh, I see.
Oh,
If you
you want
could
me to-
please use some descriptive words for those of us who are offline, because we also cannot see you.
Yes, I can attempt to also point with my mouse.
Do you see the mouse, Barbara?
Yes, that's much better. Thank you.
Yes. So the longitudinally invariant anti-KT, if you apply it in the bright frame, so these are basically DIS one jet events, and the color of these circles is kind of which jet are they in, and for longitudinally invariant anti-KT, which is basically what we use at like the LHC, it doesn't reconstruct a jet in this event. Centauro does reconstruct a jet at low PT. And then there's also a spherically invariant formulation of anti-KT that has been used in like E+ E- collisions. But the difficulty with that is that it's not longitudinally invariant, and you also get a kind of second jet popping up in the proton going direction, which is not so nice. So now we're going to do event grooming, which is kind of a new type of concept. We're not clustering jets and then grooming them. We're grooming the entire DIS event. And what you can do with this is very similar actually to the kind of prescription in PP, which is we have some radiation, like in the proton going direction, that we don't necessarily understand very well because it's very hard to measure. And we want to kind of reach to the point where we have just the radiation that we can kind of understand relatively well. And so, by using Centauro and then kind of opening back up the clustering tree, you can kind of do basically something very similar to what soft drop does in proton-proton collisions. The kind of grooming condition is almost exactly the same. The only difference is instead of using PT as you do at like a hadron collider, use this momentum fraction of the virtual photon Z.
Henry, I'm
yes.
confused. So you're talking about iteratively declustering, but you just
Yes.
told us that you don't do jet finding. So what is it that
Yes.
you decluster?
Yes. So you don't select something as a jet. You cluster the entire event using the jet algorithm. So
Well-
you produce a tree of subjets and things.
So you
Eventually-
assume that they're all part of one jet?
Basically, yes. You cluster the whole thing as if it was one big jet.
I see. Sounds
Um,
goofy to me, but okay.
Yes, it absolutely is goofy. I completely agree. But it has some very nice properties that I'll kind of get to. So this Z, this momentum fraction Z, is kind of an important quantity in general. So if you're very collinear to the photon, you have a Z roughly equal to 1. You have large Z. And then if you're soft radiation or you're anti-collinear to the direction of the exchanged photon, then your Z is very small. So what basically happens when you do this grooming is you're requiring the two branches that you're comparing to share Z, roughly equally. And what that does is that it basically removes everything that has small z, which is this soft radiation and radiation that's anticollinear to the virtual photon. And what it kind of does is that you end up with the case where basically these groomed events are analogous to groomed jets, because you've removed the stuff in the DIS event that is not jet-like. So here's
What happens if there are two jets?
Yes, that's a very good question. So in event 3, in this diagram, you can see what happens if you have more than one jet. So the left event, these are EIC energies, so the multiplicity is a little bit lower than HERA. But you see in these kind of first two events that you're nicely isolating radiation associated with the struck quark while removing radiation associated with the proton. Similarly, in event 2, you see some soft radiation being removed. And then in event 3, this is actually basically a DIS dijet event where you've removed the proton going radiation, but you've kept these two jets, brightly as some part of the struck parton, so to speak. And a lot of this is kind of rooted in the naive quark parton model. But if you have suggestions to improve it, please speak up. We don't have underlying event in EP collisions. To a very good approximation, we don't have underlying event. So why should we groom? There's kind of two. There's an experimental reason, and then there's a theoretical reason. First, it makes you less affected by lab frame detector acceptance. So as I was showing for these event shapes, right? Every single particle in an event, in principle, contributes. So if I try to measure an event shape, I'm very sensitive to radiation that I just didn't see in the detector. And what this grooming does, so on the top two plots are the ungroomed particle level distribution. So you can see this huge tail that goes kind of off the screen even of particles that just straight up left the detector acceptance. And then you see the plot on the left, or right, left, whichever. You see, our detector acceptance only goes up to eta of around 3.5. So we just lose all of those particles. But when you groom, you actually bring these two distributions very much kind of close to each other. So that's a big experimental benefit of the grooming, is that you're no longer sensitive to radiation that will typically leave your detector. Additionally, grooming kind of has some theoretical benefits of, in this case, event shapes have a nice property, which is that they do not have these non-global logs. And that's kind of a property which supposedly is preserved in this grooming procedure. And additionally, it gives you, was there a question?
Yeah.
Yeah.
What again is the difference between the left column and the right column?
So the left is particle level, which is the raw generator level particles that are produced in an event. And then the other set of plots is detector level. So that's where the particles were reconstructed by the detector.
Well, so now I'm confused because you say that you throw stuff away by grooming, but I guess what's happened is you've piled a lot of particle level, you've piled with the detector effects a lot more particles into eta of 3, right? Because you start the raw sits at 500 or 400, and then after detector effects, you go up to 1,000. So where do those come from?
Okay.
And why is it better? Looks
yes,
worse.
But no. So the difference is not that. So the top is ungroomed. So that's the raw yield of particles. The bottom two plots is the groomed case. And that's what is kind of nice, is that you don't have, so the kind of historical reason for that enormous spike of particles at eta of around 3.5 in the detector level is that HERA very often had the halo of the proton beam striking elements downstream, which fired, had kind of albedo that sent particles back into the detector, which were, occasionally reconstructed as being from the event. So that's kind of the dirty laundry that I just.
So it's crap.
Yes, and that stuff is additionally removed by the grooming, as you can see in kind of the bottom two plots. Okay, and then additionally, you get a tunable knob. You get Z cut where you can set it low and see what happens, and you can set it high and see what happens, which is kind of nice. So the actual observables that we're looking at here are two. We have the groomed invariant mass, which is just the invariant mass of everything, of whatever survives the grooming. And then we also have the groomed one jettiness, which is more or less the thrust that I was describing earlier. It's basically the dot product with this QJ, which is basically just the direction of the exchange virtual photon. And here I have kind of some event displays, which are showing you kind of the two regions that we have in these observables. So for both of them, there's kind of a peak to the left, which is basically DIS single jet events, which are collimated, and you can learn a lot about hadronization and things like that inside of them. And then there's kind of in the groomed invariant mass, there's kind of this shoulder that corresponds to DIS dijet events. And then in the one jettiness spectrum, there's kind of a long tail that is also corresponding to those same events. So really, these two observables are just kind of two different ways of collecting the information about the shape of the distribution of particles that you have after the groove. So we have, kind of a single jet event and a multi-jet event, high tau 1b, high groomed invariant mass in the multi-jet event, and small in the single jet event. Okay. So here's kind of a demonstration of why this grooming is actually important, because you can see, there's a very significant shift, even from eta, using eta less than 3.5, which is, almost covering the entire azimuth, almost covering the full 4 pi, you still actually incur a pretty serious deviation between the ungroomed distribution and, for a full 4 pi detector and a just slightly less than 4 pi detector covering eta of plus or minus 3.5. So now we're going to do a measurement. We have some phase space in DIS that we cover. So the measurement phase space that we're covering here is q squared greater than 150, so q of 12 or so and greater. And then inelasticity y between 0.2 and 0.7. If you're wondering why that y, I can explain more, but I'll kind of keep going. So here we have some comparisons to data. So the data is bin by bin corrected for QED effects using this kind of QED attachment to Monte Carlo event generators called Heracles, which produces a single, it produces real initial and final state radiation, as well as some virtual QED corrections. The data is actually, corrected for detector effects by just kind of doing a simple bin by bin correction as well. And the uncertainty on this data is kind of the statistical and systematic, which is very, very, very much dominated by the model uncertainty from the bin by bin correction. So we correct the data with RAPGAP, and we correct the data with Django, which are the two detector level simulations that we have. Thankfully, we have two, which is just very, very good in terms of data preservation sake. And they don't necessarily completely agree with each other, and that's kind of the dominant uncertainty here. So what we can kind of see is, so in these distributions, you see that as you increase z-cut, they kind of shift to the left. And they're additive observables, so as you remove particles, you get less. So that kind of makes sense. And these two Monte Carlos, which are probably unfamiliar to most of you, but they're kind of the standard HERA Monte Carlos. They have a lot of identical components in them. The matrix elements, the PDFs, and the hadronization models in these two Monte Carlo generators are basically exactly the same. The big difference between them is in the parton shower that they're using. And you see that they give pretty significantly different predictions for what the data should look like. And that's kind of demonstrating the sensitivity of these event shapes to things like the parton shower. Additionally, we have some comparisons to kind of the whole gamut of generators that we have these days. We have Pythia, both the Vincia and the Dyer shower, which also give pretty significantly different results. We have HERWIG, which kind of tends to kind of undershoot a lot of them tend to kind of undershoot the, kind of order alpha S kind of hard dijet event region. Sherpa kind of interestingly describes almost the whole distribution quite well, but then in the peak, has a very, very significant deviation. And so here's the lower Z cut. So the previous was the Z cut of 0.2, so that's harsher grooming. Here we have kind of a lower Z cut, so it's not quite as harsh at grooming. And you can notice as I kind of flip back between them that actually the generators kind of across the board typically tend to agree better with the harsher grooming, because in general, the thing that we don't understand very well in these generators is like the beam remnant. We don't know very well how to model that, but all these generators, they really know, they know to a good approximation what a jet looks like, because that's what we've studied and tuned them to, for decades now. So looking at the groomed invariant mass, we have kind of nice high mass agreement from Sherpa, because they have kind of its matrix element particle power at NLO, so kind of they have a pretty good description of that region. Pythia kind of undershoots the high mass region as well as HERWIG, and then HERWIG, but HERWIG actually does quite a good job at describing the invariant mass distribution of these kind of single jet events, and Pythia does a fairly good job with that as well. But notice kind of as we go to lower Z cut, if you look at like the ratio plots kind of down here, everyone tends to kind of diverge. As you groom less harshly, the agreement, once again, with the models kind of gets worse, which is kind of demonstrating that the kind of current hemisphere, the struck parton hemisphere, is described pretty well by everyone, whereas the kind of what's groomed away is not described very well. We also have some comparison to analytic predictions from Yannis Makris, who some of you probably know. So here we have, for the three kind of Z-cut values that we've measured, analytic predictions at different values of this kind of omega NP, which is the mean of the shape function used to kind of generate the prediction. And kind of really, I mean, they're not so great, right, these predictions. And part of that may be simply that these predictions are kind of, they're assuming that you basically have a single quark jet, which we kind of know, to some degree that that's not all that we have, because when we have an actual, full DIS event, you can have dijets where you've actually groomed away the quark jet, but you've kind of kept the gluon jet, and that can shift you to higher mass. And it's kind of, as you go to higher Z cut, the agreement maybe tends to improve a little bit, and the data kind of prefers the larger value of this non-perturbative shape function mean.
So when do I stop grooming?
When do you stop? That's very, very, very interesting question. We've kind of,
I know one limit. If I cut away all particles, then
yes,
experiment agrees.
So you're left with one particle.
yes, exactly.
Zero. That's the
Yes.
point, right?
Yes. Where do you stop is a very interesting question. Experimentally, we've kind of noticed that as you groom more harshly, there's kind of more room for stuff to go wrong. Like if the clustering tree isn't exactly what it should have been at particle level, then as you groom more harshly, you're more likely to kind of pick the wrong branch, or to stop early or stop late. So
I
there's
stop when the model agrees with the data.
That's a good strategy.
I think the interest, from my perspective, the interest is how things change as you change the grooming parameter.
Right.
I mean, if you really understand all the non-perturbative physics, you should get that evolution correctly. But what we're seeing is that's not the case. Good, there's stuff to learn there. I think it's how things change as you change the grooming, which is like that would be the key question.
and
So
with regard,
Henry 10 minutes.
okay, sure. And with regard to this specific prediction, it really wants to be, so there's kind of two different regions, quote unquote, described by this prediction. Where you're kind of the most precise is where 1 is much, much greater than z cut is much, much greater than the mass over q squared, which is really kind of only, the very, very low mass region at our attainable values of q squared. If you went to like LHEC or something like that, then probably the region of validity of this factorization would, there you might actually be kind of encountering the region of validity. Here we're kind of like maybe on the cusp of that. I mean, it depends how you define much, much greater than, right? But in addition, the EIC will have a fair amount of advantages in this kind of region because, I mean, at very low masses, you're even sensitive to hadron masses themselves, and you're sensitive to very small angles, which HERA was kind of not the optimal tool for studying those kinds of very, very collimated small angle differences. And the EIC, with its fantastic silicon tracker that many of you are involved in producing, will certainly probably be able to do that much better. So now I'm going to get up on my kind of EIC soapbox and talk about kind of some of the lessons that we learned along the way of doing this measurement. So this quantity like E minus PZ is like very important. It's effectively, the only way really to handle this QED ISR issue. And since we're trying to do precision, measurements of the DIS cross section as a function of kinematics, we really need to be able to reconstruct this quantity quite well. Because even if you have the electron well measured, you can still misreconstruct the kinematics if you don't have additional information to help you know when there was an initial state radiating photon. And also, if you're trying to do something fancy like a deep neural net or some kind of kinematic fitting, having this complementary information is really kind of vital. Hopefully, it'll be a little bit less important than it was at HERA. At HERA was really extremely important because it was kind of extremely difficult for them to reconstruct the scattered electron if it was below 8 GeV. So that's kind of the reason behind my cuts in Y, the inelasticity Y, which is kind of the direction, the diagonals in the X and Q squared plane. We really want, especially at EIC, to be able to reach those very high values of Y because for things like, low X physics, the higher Y you go, the lower X you can reach. And additionally, I mean, perturbative QCD predictions kind of are most precise in the high Y region typically. So it would be great to not have to do, to go to this kind of restricted kinematic region at the EIC. Additionally, I use very extensively here the bright frame, but it's very rooted in this kind of naive quark-parton, collinear quark-parton model where, the incoming parton has only momentum in the z direction, and you hit it, you hit just it and nothing else. In the proton, which we kind of know is becomes a good approximation as you go to high Q squared. But for a lot of the EIC physics, it'd be interesting to see if maybe there's some way that we can kind of go beyond the bright frame, in some way. I don't know what that way is, but it's worth thinking about, in my opinion. So regarding kind of the lessons for these observables in particular, they're very sensitive to a lot of the different aspects in the Monte Carlo models because every particle and the way that it's distributed affects your boost to the bright frame if you're using kind of the hadrons to reconstruct the kinematics. And every particle additionally has an influence on the grooming tree. And then every particle that survives the grooming contributes to your observable at the end of the day. So, as I was saying, you have this potential to over or under groom. You don't have any, there's no free lunch, right? You kind of open yourself up to more errors if you groom more harshly. But they kind of so the upshot of that is that they suffer a lot less from these acceptance effects, but they suffer more from you having mismodeled the way that the hadrons are distributed in your kind of detector correction. Additionally, kind of really none of the Monte Carlo event generators, like within the error bars, I mean, you know, in these kinds of plots, right, the error bars are in the ratio, you typically can't even really see them. And you know, they may increase to some degree, but really, I mean, you know, kind of none of them give a fantastic description of the whole phase space. And kind of a lot of the Monte Carlo authors that I've been in contact with have kind of agreed that, yeah, we haven't touched EP in a really long time, you know, we need to before the EIC. And interestingly, kind of Sherpa is actively using these results to constrain the treatment of the beam remnant in their Monte Carlo, as well as the kind of intrinsic KT from the peak region. One kind of last comment is that the H1 and Zeus model really served HERA very well. You know, by combining results from two different experiments, you know, you could reach significantly lower precision than, or you know, significantly more precise results than you know, having one single detector alone. And since the EIC is really intended to be a precision machine, and you know, everyone has been preaching this, like this is, you know, the standard preach, right? That we want two detectors. But you know, from the kind of data preservation side, I think that it makes it even more critical that we have the HERA data available to us. If you know, if DOE gives us one detector and that's our lives, you know, having HERA data analyzable, you know, it's almost a poor man's detector too. You know, spin physics, we can't really do very, you know, HERA, the proton beam wasn't polarized. So if there are spin results from the EIC that are erroneous, you know, you're kind of just, you know, figured out. And of course, nuclei also carried it. But, you know, if something in neutral current DIS at the EIC looks fishy, you know, a new observable or something like this, we can take the HERA data, you know, that hopefully will still be analyzable and do some kind of cross-check. And, you know, also kind of including Hermes in that. They also have done some data preservation as well. So to some degree, you know, HERA can serve as kind of a poor man's detector too. So in conclusion, there's a lot of physics left in old experiments. I wanted to, but didn't really get to touch on these kind of fantastic efforts that people have been putting on to resurrect the Aleph data. I think that's really kind of a fantastic effort. And they actually also did kind of a groomed jet mass measurement. And it would be really fantastic, I think, to take what has been done by H1 and kind of, you know, port it, like see if we can do an actual apples to apples comparison between LEP and H1 data. Again, you know, kind of unfortunately, the groomed event shape results they don't necessarily, you know, say, yes, the Sherpa model is correct, or yes, you know, HERWIG is correct. They're kind of all wrong in different regions of phase space. But it kind of confirms that for the EIC, EP could use some love in these event generators. And then kind of in the future, we're planning to do this double differentially in Q, because there was a very interesting prediction in the initial paper that proposed this observable that at the low mass region, the distribution should be completely independent of Q, because all you have is kind of the way that, you know, a quark jet hadronizes, and that's the only thing that affects the low mass region. So that's kind of a stay tuned. That's what we'll be hopefully doing for a paper. And yes, happy to entertain any questions.
Go. Questions in the room?
You have one Gendis, sorry,
No.
so you have one Gendis measurement. Did you compare with theory calculation?
Sorry?
Gendis.
Yeah.
Observable. You only mentioned about the mass, right?
Right.
Did
So,
you compare this with theory calculation?
The sketch calculation, you mean?
yeah, so that that actually does exist from Stefan Schumann and Daniel Reichelt. But they kind of only sent that to us in an email. So it's not really like an official, you know, published prediction. And Giannis didn't make the prediction for the groomed homogeneous, unfortunately.
Okay.
But if you know someone who's willing to make a prediction, that would be fantastic. We'd love to compare this to theory predictions directly.
Okay. Sure.
I And then, so James Bjorkine of Bjorkine X says do everything in the light front frame. Is that just not feasible here?
The light front frame. I guess I don't know particularly.
I need to
I'm not
know that.
familiar.
That sounds like a good recipe for theorists. I don't know what it means in
Yes,
experiment.
exactly, I don't either. I should
How would you
look at it.
transform your data to the light front frame?
I should
The
figure it
lowest
out.
transformation.
Thank you very much.
Maybe the bright really.
Yeah, I mean, is it the bright frame? I mean,
How do you
No, light front is.
how do you know what the boost is and what's the error on the boost?
Well, that's
If it's a very large number with a very large error,
Yeah,
Alright.
yeah.
I mean, I'll look into it. I mean,
I will
Sure.
too.
Yeah.
We should talk about it.
yeah.
Also, I have a question. Back on your slide 27,
Yes.
you said that this was like the naive quark and parton
Yes.
model, but I don't understand. Could you tell me what that means physically and what's the ideal?
Yes. So I mean, it's basically the case where, you know, I just have partons in the proton. They're just going, you know, collinear directly, you know, exactly collinear with the proton. You know, they have no PT, they have no, you know, KT within the proton, and I strike just one, right? Like, I mean, and we know, like, especially as you go to lower Q squared, you know, you have higher twist effects and all kinds of, you know, mess going on that the bright frame does not capture at all. I mean, you know, and people do use the bright frame for, you know, Q squared equals 5, you know, GV squared kinds of measurements. But to me, it's not really clear what you're doing there, you know, because I mean, it's kind of, you're not in the regime where the kind of quark parton model as formulated, you know, N years ago is actually really applicable.
so let's first go online, Shinyan then Barbara. Shinyan, go ahead.
Yes, the whole idea of doing grooming and is to trying to, at least in traditional sense, that is to get to the hot splitting where, you know, it's really the fundamental QCD process at play. And in that case, I would imagine most of the Monte Carlo, if they have implemented the correct QCD process, they should all agree. But in this case, it's not really that kind of jet grooming because you are not doing jet finding. And then you demonstrate there are certain observables that the most Monte Carlo don't agree. But do you have a sense, or somebody in this who are authors of Monte Carlo, that those disagreement is because of some aspect of non-perturbative process that implemented or is due to certain region where the QCD process implementing is wrong?
Right. So that's a fantastic question. I can speak only for Sherpa because they're kind of the people who have been interacting with us the most on this. They actually went into their model and they tuned the way that the beam remnant cluster is treated in their model, and they sent us you know, a distribution where basically it agrees perfectly with the groomed one jettiness. So I mean, that's kind of it's a question for, you know, each Monte Carlo author kind of individually. And I think that, like, with this information, you know, they could probably tell you, you know, exactly which aspect of their model, you know, needs to be tweaked in order to improve the description. But at the same time, I mean, you don't want to just be, you know, saying, oh, I tweaked this, and, you know, I mean, there's a huge number of parameters in these Monte Carlo models, right? And, you know, kind of unfortunately, these observables by their nature are sensitive to, like, you know, almost everything. So the question is really, you know, like in cohort with other observables, how well can you constrain, you know, every aspect of EPDIS? And so I think it needs kind of a more concerted effort from the Monte Carlo community in general to kind of come to terms with that.
Before we go on, let me just remind people we're going out for dinner at 6, so let me know if you want to join us. Well, and so tell me afterwards. Okay, Barbara and then Volker.
No, I have no question.
Okay. So I want to follow up a little bit on the last question and your answer. You showed us a lot of beautiful data in comparison to lots of models and talked a little bit about places the models have to tweak some of their parameters. But I'm curious, from this work so far, what would you say is the biggest physics insight you've gained?
The biggest physics insight. So I mean, I would say that probably it's the fact that fixed order corrections are very important in basically the whole region of phase space of these observables. So like Pythia here, so I mean, you could kind of tell from Pythia. Pythia in EP basically doesn't have it, the fixed order aspect of it is not really fleshed out significantly in EP. And you can see that by this kind of huge low, it goes down to almost 50% of the data in the high, relatively high tau region. And HERWIG similarly does that. Sherpa has the fixed order inputs to kind of one order higher than the other two. And that kind of produces, a much better description of the data. Additionally,
what does that tell us about the interactions in the interactions that are going?
Right. Yeah. So I mean, I guess it tells us that somehow, gluon radiation, hard gluon radiation from the struck partons is somehow more violent or more common than is expected by these models, I guess. And even in the analytic prediction, with some discussion with Giannis, he kind of posited that perhaps this is why even his low mass predictions really kind of undershoot the data basically everywhere. Because if you imagine, if I have a quark jet, it fragments in one way. If I have a gluon jet, it fragments in another way that typically gives a higher mass. So just kind of in a vacuum, the gluon jet will have higher mass than the quark jet, and our data falls to higher values than his prediction. So that's kind of a possible explanation for why these analytic predictions don't do so hot.
So do you have a question?
Yeah, Henry, could you go to the slide before your summary? I think there you mentioned HERA as a detector 2 at EIC.
Yes.
Can you elaborate? The center of mass energy is totally different. Is that right? If I remember.
Right.
Yeah. How can we serve as a detector 2? I think we really need a detector 2.
I completely agree. I 100% completely agree. However, in the enforced absence of a detector 2, to the degree that DIS is kind of universal, right? I mean, you have X, you have Q squared, and you have Y. You can compare similar Q squareds, at HERA and the EIC. Even I didn't mention this, but the EIC, the statistics, the luminosity is so much higher that in fact for this region of phase space that we're analyzing, like Q squared around 150 GeV squared, the EIC will actually have more, equal to or more statistics than HERA did, despite the, almost half center of mass energy in EP. So that's kind of the degree to which, again, it's absolutely not an apples to apples comparison, because of things like spin but if there were some, very odd result that HERA could cross-check, it would be just terrible for the HERA data to be somehow, not analyzable, like not able for us to double check that result with the HERA data.
Maybe you can call it detector 3.
Detector 3, yes. Or detector 2.5, whatever you want.
No, but I think you mentioned the word universal. I think this question of universality, also on Giannis's plot, he's got this omega non-perturbative. I think this, when you started off by saying one should look at QCD in multiple environments, I think that's really a key message here is that they're kind of testing the same phenomenon from different initial states.
Right.
Can really inform the universality of QCD.
Exactly, and certainly somewhere down the line, we will want to we will combine EIC and HERA data, right? There will be combined analyses of EIC and HERA data. And having the HERA data, actually tangible and not just sitting in some plot, a table of data that has some binning that was chosen, 30 years ago. It would be great to have the ability to, play with the data and actually use it to improve, the quality of combined analyses with the EIC.
Okay, thank you.
Okay, no more questions. Let's thank Henry.
So I'll stop recording.
Henry will be here.